Okay, in section 8.2, we're going to begin the understanding of the three-phase system by first generating a single phase of electricity, a single sinusoidal AC phase of electricity. Let's explore how that's done. And then what we're going to do is we're going to expand that to two phases and then to three phases. And then we can do a, sort of a mental exercise and go beyond that. But let's begin with a single phase of electricity and let's explore how that's generated. Here's figure 8.1 from our textbook. Before we dig into this, let me do a little explanation. This area here that I am putting yellow into is something that we call the stator. And we call it the stator because it's not moving, right? It's stationary. And it is composed of ferromagnetic material, usually laminated plates, always laminated plates, to lessen the impact of what we call eddy currents. But anyway, so this is a cylinder with a hollowed out area in the middle. And what we can do within that stator is we can cut slots in there. We can cut slots in there and we can lay conductors in those slots. So when you look at this thing, when you look at this thing, here's this conductor here, and it would run the length of that stator. Think about that stator, and looking something like this. And so that conductor runs the length of that stator and terminates back on the other side here. So here's this conductor, runs from one end to the other, and it terminates from that particular point. In addition to that, and we'll call this, we'll put a designation on here. We'll call this, say this is the beginning, we'll call it A, and then it terminates here at 1. So this is phase A, and this is the 2 points where it terminates. And we notice that, if we look at this in terms of degrees, this is 180 degrees from here to here, right? 90, 180 degrees from that point to that point. In addition to that, what we have is a magnet, okay? And here's a magnet, and this magnet is able to rotate freely, and we've got some way to cause that magnet to turn within that stator. And we know back from our earlier studies that anytime you have a conductor that is exposed to a magnetic field, it will generate a voltage. So here is this rotating magnet, and we're showing it turning clockwise, and it's turning in through there. Well, there, of course, is magnetic flux that is, coming from this magnet. We normally show those lines like this, right? In that way. But anyway, as that flux cuts across that conductor, it's generating a voltage. And we can actually quantify this, going back to chapter 2.25, in, before then, actually, of course. But anyway, this idea, this generated voltage, I don't know where I came up with a G, but this generated voltage across this coil, I'm going to get this right a minute. This generated voltage, A1, that would occur across that coil would be equal to this equation, which is equation 2.25. This is the magnetic flux density measured in Tesla. This is the length of the conductor that is exposed to the magnetic field. Okay, and that would be, we look again and we're thinking of this in terms of, that coil running the entire length of this thing and then terminating back. It would be these areas that are exposed to the magnetic field. The length of the coil or the conductor that's getting cut by this magnetic flux. And then the other part of this is the speed. Okay, the peripheral speed of the revolving poles. How fast is this field turning? So all of these are proportional, right? If I increase the flux, I increase the voltage. If I increase the length, I increase the voltage. If I increase the speed, I increase the voltage. So all of those things together designate or determine what the voltage is that will be induced across that coil. All right, so let me stop with 8.2 and we'll make a part 2 and finish this up.